Right, good morning. Looks like we're back. We did the assessment on Monday for the ecosystems. I'm not going through the assessment today. That'll be in the Teams lesson on Friday. I'll go through the standard and the higher paper. I'm really chuffed with how you're getting on with the team stuff. You seem to be doing really well with that, asking loads and loads of good questions, so well done. Today we're going to start on the forces topic, and we are hopefully going to get that finished before the end of term. There's not that many lessons in it, and I think we've got enough time to do a good job, and that's good because forces is a real key part of all science, really, especially your physics. So let me shrink myself and I will go through the learning objectives with you. The learning objectives may at first seem quite simple, but not really as simple as you might think. Especially this one. We're going to recall the effects of forces on an object. So what is the effect of applying a force on an object? We're going to learn to name forces and classify them as contact and non-contact. That one's easy. And recall how to measure them and their units. That one's easy also. But this first one, not so straightforward. So the bulk of this video will be about that. So let's use this example of a picture of two people on a bike to look at what are the effects of forces. Now, if I was to show you that picture and I was to say, oh, look here, we have a force, forward force on both of these bikes. What will happen to the bike? I can guarantee you 90% of you will say the bike will move forward. Maybe a couple of you will say the bike will speed up or accelerate, which would be the right answer. Now, what I want to identify straight away is the idea that we can't talk about forces as being things that make you move. All right? Obviously, if I'm not moving now and somebody pushes me and applies a force, I am going to move, so they can do that, but we don't talk about movement, we talk about changing speed. So if someone did come and push me now, I'm going from a velocity, a speed of 0, to a higher speed as I move. So if somebody asks you what is the effect of applying a force on something, it makes it speed up. Now, of course, we can have the opposite. You know, if something's moving towards me and I apply a force in the opposite direction, or these people on the bikes apply the brakes onto the wheel, that's going to slow them down. So a force can speed you up or it can slow you down, so it can change your speed. Please don't say move, please say forces change your speed. And if you can put the words accelerate or decelerate in there as well, even better. Now, this is a second take of this video because I fluffed my lines and got a little bit wrong on the last one. So my only can is already pre-crushed. I had a fantastic experiment where I showed you how strong I was and I crushed this can. I changed its shape by squeezing it. If only you could have seen it. Now, why have I done that? Well, because a force is needed to change the shape of the object as well. So we know forces speed things up or slow them down, they change the speed, but they also are required to change the shape of an object. And forces are also needed to change the direction of an object. So they're the three things forces do. Newton summed it up in his first law. He said an object that is in motion remains in motion unless acted upon by an external force. But you know what? He never was one that was good with words, was he? That sounds like a lot of fluff. Let's just imagine a force as being something that speeds things up, slows things down, changes the direction, or changes the shape. Let's see what other examples we've got on here. So let's have a look at the diver. Now the diver here, he has 4 forces acting upon him. And you might recognize the fact that the bigger the arrow, the bigger the force. And you might see that the upthrust and the gravity are acting in opposite directions, but they seem to be equally sized, balanced forces. You might see that the forwards and backwards seem to be equally sized. They are balanced forces. Now, when we have a situation like this where there's more than one force, not like the bike, right? The bike just showed us the one force, and we know that's going to make the bike speed up. It's going to not move, it's going to make the bike speed up. Well, what's going to happen if we have these forces applied? And again, this is another area, a little bit of a misconception. People will often look at that and they'll say, the diver's not going to move. Now, that's not necessarily true. Not necessarily true. If this diver was already swimming when the forces around him kind of arrived at those sizes, if he was already moving when the forces around him became balanced, then let's think about what a force does. It changes your speed, or it changes your direction, or your shape. Now, if these forces are all balanced around him, they cancel each other out, then his speed isn't going to change. So if he was already moving when he got to this point, he's going to carry on moving. So you can have balanced forces upon you and you can be moving. So for example, if you're driving down the motorway in a car and you're at a steady speed, the forward force on the engine is going to be equal to the frictional forces trying to slow you down. They are balanced, so your speed doesn't change. It stays at what it was. To accelerate, you've got to actually put your foot on the gas and increase that forward force. I said gas, not accelerator. Shocking. If you want to slow yourself down, you put your foot on the brake and you increase those frictional forces. So to summarize, what seems like a simple learning objective that maybe I've made seem a bit more complicated. Recall the effects of forces on an object. They change an object's speed, they change an object's shape, and they change the direction an object is traveling in. We'll get more into balanced and unbalanced forces in the next video. Now here, classify forces as contact or non-contact. And that really actually is as simple as it sounds. If I show this diagram here, now we have, let me see if I can just make that a little bit bigger for you. Look at that. Now, we have this little buggy here, and we have the force of gravity pulling an object down. Now, gravity isn't something that reaches out and physically touches an object. If I had a ball in the air, it's going to fall, and we can't see anything reaching out and grabbing its hands on it and pulling it down. So we describe that as a non-contact force, just like you might describe two magnets. You put two magnets together and they can attract or they can repel, right? And they will do that without necessarily touching each other. So any kind of force that acts over a distance where things aren't touched, like this one here, like the static electricity, the static charge on this balloon is attracting the hairs on the cat, right, without touching them. We call that a non-contact force. And our non-contact forces are static electricity and gravity and magnetism. They're the three big ones while we are going through school. They're the three big ones that we need to really be aware of. Now, whoops, what have I done there? Magic. Now, the rest of them, contact forces, easy, right? If you push something or pull something or twist something, right? If you or friction where something slides over something else. If two things have to touch for a force to be applied, we call it a contact force, all right? And that will include everything that we ever see in school other than magnetism, gravity, and static electricity. Third objective, I forgot what it was. Recall how to measure forces and masses and their units. Absolutely. Well, if I bring this diagram up here, this, oh, I'm having a computer problem. Right, there we go. Let me see if I can zoom this up. It's like live TV, isn't it? You're seeing everything go wrong. There we go. All right, let me zoom that. Right, this here is the kilogram. When we talk about mass, we say that mass is measured in kilograms, but who decided what a kilogram was? You know, who actually decided what we're going to call a kilogram? Now, there are complicated mathematical explanations for why we arrived at the answer we did. And we'll save all those for another day, and it's all thanks to Isaac Newton. But essentially, there is a block of metal, and it's kept near Paris, it says there, in a safe, and we say that that block of metal has a mass of 1 kilogram. And anything that has a mass of more, of double that, will have a mass of 2 kilograms. Anything that has a mass of half of that will have a mass of half a kilogram. So a mass basically just talks about the amount of stuff that there is, all right? And if you've got a certain amount of stuff, we just say you've got a mass of 1 kilogram. If we have twice that, we'll say you've got a mass of 2 kilograms. So if we look at the learning objectives, the units of a mass here is the kilogram. Now, I will, before this topic is over, explain why I've made such a song and dance about that in this video, because it is more complicated than that. But for this learning objective, we just measure mass in kilograms. It's just how much stuff we are. Now, notice if you take me, for example, I'm made of a certain amount of stuff, I've got a certain mass. You put me on the moon, the amount of stuff I'm made out of isn't going to change. My mass isn't going to change. You put me on Jupiter, my mass isn't going to change. I'm going to be made out of the same amount of stuff. But because those planets have a different gravitational pull, yeah, that force pulling us down, my weight will change. If I'm pulled down with a bigger gravitational force like I will be on Jupiter, I'll actually weigh more. If I'm pulled down with a smaller gravitational force like I will be on the moon, I would weigh less. And anybody who, I was watching Superman last night with me, or the night before with one of my daughters, and Superman was kind of based on the science that we're talking about now. Superman come from Krypton, and Krypton was a massive planet with a huge gravitational pull, which meant that even, you know, little things like this little wooden token here, the gravity on Krypton would be pulling it down so strongly that it would be very difficult to pick up. It would weigh a lot. And that's why Superman is so strong on Earth, because his body is designed to live on a planet with a massive gravitational pull. But on Earth, the gravitational pull is a lot less. So just like humans going to the moon, we'd feel things are lighter because the gravity's less. He comes to Earth from Krypton. He thinks things are lighter because gravity's less. So, no idea how I got onto that. No idea why I was talking about that. I'm sure it was relevant when I started. So, how to measure force and masses in the units. We've talked about mass. How do I measure it? We just use a microbalance. Bang. So, forces. What are the units of forces? Well, we talked about Newton and his first law not so long ago. And the unit of force is, you know, attributed to him. We call it the Newton. Neutow. Okay, so weight, which we described as a force, will be measured in newtons, but our mass, which is how much of us there is, will be measured in kilograms. So really, when we go to a shop and we say, can I have 10 kilogram worth of potatoes, you know, if you're making a lot of chips, then we're asking that in the wrong way. We shouldn't be asking for 10 kilogram worth of potatoes. We should be asking for weight in newtons. But the general public don't do that. We do ask for things in kilograms. We do ask for things in mass. So that is a little contradictory to what you're used to in everyday life. You don't walk up to someone and say, I weigh 800 newtons, but you might walk up to them and say, I weigh 80 kilograms. You give them their mass. And we call it weight, and it's wrong. So it's going to take us a little while to separate those two. Weight, which is a force, is measured in newtons. Mass, which is the amount of stuff we're made of, is measured in kilograms. But we'll get to more of that later on. Now, how do we measure force? Well, we also have scales for measuring force. So whereas we have a microbalance or a balance to measure the mass of something in grams, we also have balances that measure the weight of something in newtons. And we'll talk more about the link of those in future. You may have used in school the little spring balances, the Newton meters. So we can also use a Newton meter. But for now, I think we've kind of explained everything. The take-home points from this lesson, because I have waffled a lot today, the take-home points are the effects of forces on an object, they will change the speed, the shape and direction. Forces can be classified as contact if there's touching involved, or non-contact if not, and the non-contact forces are gravity, magnetism and static electricity. And the units of force are newtons, the units of mass is kilograms, and we measure them both with scales. Okay, so they are the take-home points. Right, let me close that, and back to me again. There'll be some worksheets set with this video as well for you to have a go at, and then just remember on Friday on the Teams lesson, if you bring your assessments, and I'll remind you about that in class charts as well, but if you bring your assessments, we'll be able to go through those in the session. So good luck. Bye bye.